Hello, my name is Roy Simpson. I'm an instructor of mathematics at Cosumnes River College in Sacramento, California. In this lecture, we're going to cover a little topic in intermediate algebra called algebraic equations. Specifically, we're going to focus in on equations and formulas in this part of this lecture. This should be a review of elementary algebra, but I'm still doing it because I think that it's beneficial for students in an intermediate algebra class to have the option to review algebraic equations from a more advanced perspective. That being said, there are a few prereqs here. We have arithmetic, that's definitely a prereq, and as well we have expressions. You have to know what an expression is, and if you don't, then please go to my previous lecture on algebraic expressions. And finally, you should have already taken an Algebra 1 or an elementary algebra course. Now we're going to go ahead and start this section with a simple definition of an algebraic equation. Algebraic equation is essentially a combination of variables and constants with operations and an equal sign. And this is an important part, that we also have an equal sign. There's actually a very easy way to think of algebraic equations, other than just the fact that, for example, anything of the form like 3x is equal to 12, or pi times x minus x squared is equal to 3y plus 1. These are both equations because they have equal signs, they have variables, they have numbers, and they have operations. Addition, multiplication, squaring, all that stuff, those are all considered operations. However, it also turns out that algebraic equations are essentially statements that are either true or not true. They're essentially the mathematical equivalent of a claim that somebody makes, like in English. Somebody who's just speaking with spoken language instead of mathematics would say something like, I have $300, or the amount that I have in my wallet is $300. That's either true or not true. That person's name is Bob. That's either true or not true. That can be proven or disproven. You can just ask the person if their name is Bob. So those type of statements are the mathematical or the English equivalent of an equation. And so I wrote a couple of them out. His name is Bob. That can be proven or disproven. We are eating Oreos, something like that, right? That's something you can prove or disprove. However, expressions are very much different beasts. And easiest way to see expressions in language versus what we do in mathematics. Mathematics, an expression is like 3x. It's neither true or untrue, it just is. So an expression in English is like hi, or blue, or I don't know. It's pretty much anything. Wow. These are things that you state, but it's not like somebody says, oh, that person said, wow. I wonder if that's true or not true. You can't, I mean, there's no truth or untruth to it. It just is what it is. So equations, the language equivalent, are things that can be proven or disproven, and expressions, the language equivalent, are things that just are. You know, when somebody points at something and says, hello. I mean, that's doesn't have any type of meaning or proof or disproof. So the idea behind equations is to solve them, to find out what the unknown is, essentially to prove something about that. We are eating Oreos, so let's go ahead and prove that. So we look around for the bag of Oreos, they're empty, and somebody has chocolate in their teeth. That pretty much is an indication. So let's go ahead and take a look at a little sub-example I have here. What can we say that is common about the following equations? So we have equations 1, 2, and 3 here. And they're all different equations. They all look different. The last one, it tells us explicitly what x is here. X is 2. The second one doesn't tell us explicitly what x is. However, if you look at that, if x were 2, it'd be 2 times 6, or 12 on the left-hand side, which would make this a true statement. Along the same lines, actually, the first one, if we were to let x equal 2, I always do my math with a question mark and the equal sign because I think just because it makes it clear that we don't know if these two sides are equal yet. That would be 10 minus 8, which is 2. And on the right hand side, negative 2 plus 4 is 2. Oh, which is a true statement. So what these three equations have in common is they all have 2 as a solution. And in fact, they all have x equals 2 as a solution. Often, by the way, in mathematics, people will say solve this equation. They won't say solve for x or solve for y. They'll just say solve this equation. If they're asking you to solve an equation, it's implied it's for the only variable that's in that equation. If there are two variables, then you need to ask them, what variable do you want me to solve for? But anyway, back to this. They all have x equals 2 as a solution. Well, if they all have the same solution, we could say that they're kind of from the same family. They have the same set of genes or DNA, I suppose, because they all have the same, well, solutions. So let's go ahead and define what that means. These are all called equivalent equations. And what are equivalent equations? Equivalent equations are equations, and you see my shorthand, EQNS means equations to me, having the same solution. And maybe I'll even be more specific here, or I suppose more general. Just depends on how you think of it. I'll say having the same solution set, same set of possible solutions. Those would be considered equivalent equations. So if I go back to that previous example, while these all have the same, or because they all have the same solution, x equals 2, these are all equivalent equations. And as I mentioned before, I consider them to be of the same like genetic code. They're born of the same species or whatever. So that's a very good way to think about it. Now we're about to embark upon some examples here. Before we do, we want to get very specific. There's a lot of different kinds of equations out there. I mean, tons of different kinds of equations. In fact, I could just write a few down here. So examples, these are all going to be equations. You've seen some examples I've written down before, like 3x plus 1 is equal to 7. That's an equation. X squared plus 5x plus 6 is equal to 0. That's another equation. The square root of x minus 3 is equal to 10. That's an equation. X over x plus 1 is equal to 5. That's an equation. So we have a bunch of different equations here. But each of these equations are very specific on how you would solve them, how you would approach them. And so we like to label these, give these names. We like to, in mathematics, we like to box things up. We're very prejudice, I guess you could say, in mathematics because we like to group things and kind of label things. But it actually helps us with our language in mathematics so that you know specifically what we're talking about. And one of these, specifically this one, is the one we're going to start off with. That's a linear equation in one variable. A linear equation in one variable is an equation of the form ax plus b is equal to c. And often, most mathematicians even leave off the c, and they'll just write that as ax plus b is equal to 0. The reason why is because if you just consider for a moment, as an aside, 3x plus 1 is equal to 7, I could rewrite that by subtracting 7 from both sides as 3x minus 6 is equal to 0. And there you see that's an ax plus b is equal to 0 form from the fact that we started with an ax plus b equals c form. All right. So linear equation one variable is defined to be an equation of the form ax plus b equals c, where I should mention a, b, and c are all numbers. Are numbers. They're constants. And a, well, let's suppose a is not equal to 0. Main reason why this last condition is on here, by the way, is that if a is equal to 0, just pretend it is for a moment, then you don't have any variables because 0 times x would make that term disappear. So you would just have some constant equals a constant. There's no variable there. That's why to be a linear equation in one variable, we need that variable to survive. Okay. And again, that 3x plus 1 equals 7 is an example of a linear equation in one variable. This second one is not because it's not an x, it's an x squared that you have in there. This is not because it's a square root of x. This is not because you have a fraction with x's in it. So x is specifically in the denominator. So I'll say not linear. Actually, I'll just do that. These are all nonlinear equations. And we'll approach kind of how to solve stuff like that later on in the course. And you'll see that the technique that I use to solve equations, I generally only like one technique to solve every equation I could possibly do until I get to more general equations. So I'm going to stick to a favorite form of mine to solve equations. Speaking of solving equations, let's go ahead and solve this equation right here. Now, the first thing you want to do whenever you go to solve an equation, so maybe I should just write a little method here, even though I'm not a big fan of methods, but I do want you to know that there is a technique to solving equations. Maybe I should say to solve an equation. The first thing I generally do is clean up each side. I'll put that in quotes. Clean up each side. What that means, at this point in mathematics, you should already know this, is essentially make sure you have no parentheses, no grouping symbols. You combine like terms. So on each side, that's what we're going to do. So this would imply, and by the way, in your math instructor would be very impressed if you stick with this notation. This equation is not equal to another equation. It's not like that. You have an equation and you do some work to make it an equivalent equation. So this implies that little arrow means implies, that 3x minus 2x minus 2 is equal to a negative 2x plus 4, which implies, when we combine like terms on the left-hand side, 3x minus a 2x is a single x. So we get that far. So we've cleaned up both sides. There's no grouping terms. All terms have been like terms have been combined. And I went ahead and wrote those instructions over there. Distribute across grouping symbols, combine like terms. The second thing I do, now that I've done that, and I can't go any further, is I get all my variables on one side and all my constants on the other. In fact, I think I would probably, it's better to say just like get all your variable terms on one side. So I look at this equation, I think to myself, well, what would be better? Would it be better to get this single little x over to the other side by subtracting x from both sides? Or would it be better to add 2x to both sides? I like to keep things positive. So what I'm going to do is go ahead and add 2x to both sides. I'm not 100% sure you could see. That's kind of hard for me to see even. But we'll do that. Maybe I'll change colors next time. So on the left-hand side, we now have 3x minus 2. On the right-hand side, we just have a nice little 4. And I am assuming that you know all these operations with equations. And I know I'm taking my time here, but I need you to kind of see my thought process. At this point, I take a look at this. I know how to solve this equation. So you should make a little note here, though. If there's only one version of your variable in that entire equation, then you can untie the knot. And this is where a lot of students hate my method initially, but then love it in the long run. It's because students at this point know what to do with this equation. They know they add 2, divide by 3. Okay, great. But I want to show you kind of a method that will be extremely useful for future topics in mathematics. The idea of an equation is that somebody grabbed that x, and instead of telling you exactly what it was, in this case x is going to be 2, I know that, but instead of telling you, oh, by the way, x is 2, they've tied it up in a knot. They've essentially attached to it a 3 and then subtracted 2 from that. So they've hidden the value of x from you by doing that to it. So what you need to do is untie it. Now, you can think of that as somebody tying a knot, that they had x and then they started tying it up with a 3 on it and then tied it even to a knot even further by subtracting 2 from that. So what I do is I list out what happened to x. I know that most people already know how to solve this and they want to just skip this, but I'm telling you, very, very important to just think of it this way, because there are going to be a lot of topics in an intermediate algebra course, trig course, pre-calculus course that's going to rely upon something called the inverse. And that's a very advanced mathematical concept. If you start viewing mathematics the way I'm teaching it right now, you will, in the long run, benefit. Once you reach inverses, you'll be like, oh, I totally know what that does. It's just you're untying the knot. That's all an inverse does. So right now we're going to develop an inverse. All right, so what happened to x? Well, somebody took x and they multiplied it by 3. And then after they multiplied it by 3, they subtracted 2. Order of operations, right? And this is what I like about saying it this way, is because you're following the order of operations. If I just went straight to solving this and saying, oh, I add 2 to both sides, divide by 3, it's counterintuitive because you are not following the order of operations. The order of operations says do anything with addition or subtraction last. So I like to stick with one thought process throughout an entire course if I can, and my thought process is the order of operations. Well, somebody had to follow the order of operations to hide this x from you, so what they did is they multiplied it by 3, that's the multiplication before addition or subtraction, and then they subtracted 2. Now we're going to untie this. So this is how they made the knot. Now we're going to untie. And when you think of a knot, when you untie a knot, the thing you untie is the last thing that's been tied. So the last thing that was tied was step 2. That's the last thing they did, right? So to undo a subtraction of 2, we're going to add 2. Once we're done untying that, we'll hop up this ladder here. To untie this multiplication by 3, we do the inverse of multiplication by 3, which is division by 3. This is my roadmap to untying this knot. I'm going to add 2 to both sides to get 3x is equal to 6. And then I'm going to divide both sides by 3 to get x is equal to 2. I know it's extremely lengthy to say out loud, to go through and do all that, but the fact is, this will help with tons of equations in the future. Radical equations, some rational equations, logarithmic equations, exponential equations, stuff that you haven't seen yet, trigonometric equations, some equations in pre-calculus, solving some calculus problems. It's all throughout that. If you follow this method, as long as you have this satisfied, that there's only one version of your variable, you can do that. And often that's the case in mathematics. Now, not all the time, but it can be the case. Now, in the last example, we spent quite a bit of time going through it, and I still think it's very beneficial to have gone through all that. But the fact is that we need to speed up a little bit, right? So let's go ahead and tackle this next example. First of all, first step is always to clean up sides. And you can see that both sides are cleaned up. There's nothing really you can't combine like terms on the left side, and there's nothing to do on the right hand side. So the second thing we do is move variable terms to one side, so isolate, I guess you could say, variables. It's not completely isolated, actually. I'm just going to decide to move all my variable terms to one side. I can move them all to the right hand side. Yes, I could do that. I tend to not do that actually out of habit, but you could totally do that. You can subtract 2.4 from x from both sides if you want. I'm going to just keep my habit of keeping my variables positive, so I'm going to add 3.7x to both sides. Not necessary though. You could have done it the other way, and most people would have. I just have this bad habit of going about it this way. On the right hand side, you see that the 3.7x's will cancel. On the left hand side, what do I get? 5 6.1x plus 8.1. By the way, you'll often hear me just do math in language, or 5 6.1, that type of thing. Okay, and at this point, I want to untie. I see I have one version of my variable, so I'm going to start the untying process. So I ask myself, what happened to x? What did somebody do to x to tie it up like this? Because they obviously didn't tell me what x was. The first thing it looks like they did is they multiplied it by 6.1. The second thing it looks like they did is they've added to it by 8.1. So I'm going to untie that by untying the last thing they did, that knot. Say I tied x up in a knot. So I'll untie that last step there by subtracting 8.1, doing the inverse of addition. And then after I'm done undoing that addition, I'll undo multiplication, which is division, dividing by 6.1. Now here I go. I'll subtract 8.1 from both sides to get 6.1x is equal to a negative 8.1. And then finally, to untie this last little bit, I'll divide both sides by 6.1. And this will give me x is equal to a negative 8.1 over 6.1. Now, you don't want to leave a fraction with decimals in it. I'll often say this anyway, but I just want you to make sure that you do not stop here, because this would be absolutely horrible notation. So grab a calculator and figure out what this is. Let's see. So I boot up my calculator here. It's negative, what is it, 8.1? Divided by 6.1. Remember, your calculator has a special negative button, so don't use a minus sign for negatives. Hit enter, and you get some decimal approximation. Let's go ahead and round this to the nearest hundredth. So we'll have a negative 1.33, right? That 7 rounds that 2 up, so negative 1.33. And a little word to the wise here. When you're doing this, it's roughly equal to a negative 1.33. It's not exactly equal to it. So it's very important that you let people know it's roughly equal to a negative 1.33. As far as examples for solving linear equations in one variable, this will be our last, and then we're going to spend a little bit of time on formulas. In this one right here, it looks like the very first equation that we solved, but there's a subtle difference, and it's such an important example I need you to pay attention. So first thing we do is clean up both sides. I'm not going to write that step down, I'm just going to do it. And this implies when we combine like terms on each side, we'll have a single x minus 2 is equal to a single x plus 20. And then before we can start untying the knot, we need to get all our variables on one side. Well, I'm going to go ahead and subtract this x from both sides. And we get the following. X minus x, that's gone. X minus x, that's gone. A lot of people, by the way, I've noticed this written, they think that there should be an x, so they write 1x over here. X minus x is nothing, and the x minus x over here is nothing. So you get to negative 2 is equal to 20, and you ask yourself, is that true? You should always stop every single step. You should just pause for a moment and say, can I go any further, or is that true? That cannot be true. So every once in a while, we'll get an equation somebody gives to us, and it just can't be, there's no possible way it can be true. So this is called a contradiction. In mathematics, we often call an equation with no solution, or an equation that reaches some type of logical issue like this, a contradiction. And this is the equivalent of saying to somebody, I am a fish. The fact is, I'm not a fish. right? So that is not a true statement. I could say I am a person, or I am a human, or I have brown eyes, or something like that. Those are true statements. Somebody could prove it, but this can't be proven because it's not true. So it's a contradiction. And I suppose I should mention, every once in a while you get stuff like, I didn't have this in my example set, but I thought I'd go ahead and just give this here. Sometimes you'll get stuff like this. Solve that, and when you do try to solve that, you get all the way down to x minus 2 is equal to x minus 2. You'll subtract x from both sides and you get negative 2 is equal to negative 2. And that is always true. That gets a special name as well. If something is always true, we call that an identity. So just to let you know that when you're solving things in mathematics, if you get to a statement where a constant is equal to a constant and they're not the same number, like this one over on the left, you know that's not true. It's a contradiction. But if, on the other hand, when you solve an equation, all variables end up disappearing and you get a constant equals a constant and they're the same number, like negative 2 is equal to negative 2, that's always true. We call that a mirror image or an identity. Now, the last few topics here, or last topic, I guess you could say, we're just going to deal with some formulas really quick. And to define a formula, it's essentially an equation with, well, I suppose it would be two or more variables. It's a very general, broad statement, by the way, but there's tons of formulas that we know in mathematics. D equals RT is one of them. C squared is equal to A squared plus B squared. Now, this formula is not always true. It's only true for right triangles, where C is the hypotenuse. There's a ton. There's a ton of formulas in mathematics, and I know that students feel overwhelmed. Oh, I have to memorize so many formulas. In general, you don't have to memorize too many. You have these principal, rate, time. There's a lot of them. Anyhow, so these are all examples, and notice there's just a bunch of variables in them. In this lecture, just the next two examples, in fact, that's it. We're going to concentrate on solving formulas for specific variables. Like in this example, we're gonna solve this formula, which is t equals 4j times the quantity j plus 3k. We want to solve that for k. The rules here are kind of like the same rules that you would follow if you were going to solve an equation. You want to clean up sides. So let's go ahead and start there. I mean, you wouldn't you want to make sure you do the easiest route, so it takes some experience doing this, but the fact is I cannot easily solve for k because it's mixed up in this business. So I'm first going to clean up each side. So I have, this implies that t is equal to 4j squared, right? J times j is j squared, plus 12jk, because that's just me distributing across the parentheses. Okay. And the second one is kind of the weird one in this case, which is isolate the variables, or in other words, if you have several different versions of k, get them all on the same side. Well, we really only have one version of k. It's this one right here, and it's already by itself on a side. So now we can start untying. If we only have one version of k, we can immediately start to untie. So let's ask ourselves that question: what happened to k? Notice I'm not asking what happened to x because that's not what we're solving for. So if I look at this equation, what happened to k, let's see, somebody came along and multiplied it by 12j. Right? They just attached a 12j right on there. And if you take a look at this equation, there's another way you could have written it. You could have written it as 12jk plus 4j squared. And some people like to rewrite it like that. And when they do, they see, oh, okay, well, after they multiplied that by 12j, they then added 4j squared to it. So now I'm going to untie that. That's how they hid the value of k from me. So I'm going to untie that. So to untie the second step there, the last step they did, I'll subtract 4j squared. And to untie the first thing they did, I'll divide by 12j. So let's go ahead and do that. That's my roadmap. So here we go. Let's see, I'll subtract 4j squared from both sides. Everything has to be done from both sides. And the left-hand side, t and j are two totally different variables, so they can't really subtract easily. So you're just left with t minus 4j squared. You can't combine those two terms. On the right-hand side, the 4j squareds cancel, and you just have this 12jk. So after we're done subtracting 4j squared, I tell myself, okay, now I need to divide everything by 12j. So I will divide everything. This object right here by 12j, and this side by 12j as well. And when you do that, you get the following. T minus 4j squared all over 12j is equal to, on the right hand side, the 12's cancel and the j's cancel, and you get k. And look, that's exactly what I wanted to solve for. A word to the wise here, when you're asked to solve for a variable, like in this case it was k, make sure that that variable is by itself on one side of your equation when you're done. You shouldn't have k's all over the place. You should have a k on one side and that's it. If you have a k on both sides, you've done something wrong. Another thing that that some people might do, they might ask, well, when I did this, I got k is equal to t over 12j minus, let's see, j over 3. That is equivalent, okay, to this answer. It turns out that when you have a fraction like a plus b over c, that's the same thing as saying a over c plus b over c, right? These have the same denominator, so their numerators just add. Well, that means that if I have a fraction like t minus some picture over 12j, I could split this apart to t over 12j minus 4j squared over 12j. And this one, the first fraction is completely simplified, but the second fraction, the 4 goes into 12 3 times, and the j's will cancel to give me only a single j up top. That's how you get that business. So they are equivalent. Neither is more acceptable than the other. It's just two different representations for the same thing. So let's go ahead and try one more, and then we'll be done with this lecture. Let's go ahead and solve a equals pi rh plus pi r squared for h. Well, the first step we want to do is clean up the sides, but if you take a look at the problem, there are no like terms. Like there's no parentheses on the right hand side, nor are there any on the left. And on the right hand side, you can't just add these two objects together because they're not the same exact pictures. So there's really nothing I could do. The second thing is to get all h variables on one side, but they already are. Right? All my variables, all my terms with h's are already on the right hand side. Okay, so I guess I just need to untie this. And I can say that because there's only one version of h. Again, back to my method where I keep saying, no, there's only one version of this, so let's go ahead and untie that. So let's ask ourselves, what happened to h? Now, obviously, you don't have to write what happened to h. It's just, I do, that's all. So the first thing that somebody did when they were trying to hide the value of h from me is they multiplied it by pi r. Right? That's that picture they placed right in front of h. And then after that, they added to that with pi r squared. I already know that's an area. Okay. So let's go ahead and untie what they did to tie up h. So I'll start with the last thing. I'll start by untying the last thing they did. They added pi r squared. I'm going to subtract pi r squared. And the very first thing they did is they multiplied by pi r. I'm going to divide by pi r. Okay, so to start untying this knot, we'll subtract pi r squared from both sides. I'll go ahead and do that. Let's get the right pen color. So subtract pi r squared from both sides. Following my method, you really avoid a lot of extra work, honestly. A lot of extra thinking, really. Let's see, the right hand side is just pi r h. So that's the first thing we do to untie the knot that they tied up. The last thing we do here is to undo that multiplication by pi r by dividing both sides by pi r. So I'll divide the right hand side by pi and by r, and again the left hand side by pi and by r. And you will see, by the way, I forgot my implication signs. And you'll see that the left hand side is a minus pi r squared over pi r. And the right hand side, the pi's cancel. Pi over pi is just 1, and r over r is just 1. So that's 1 times h, or in other words, h. Now, again, this is perfectly acceptable as an answer. However, some might want to separate this out and say, oh, that's like a over pi r minus pi r squared over pi r. The only reason why somebody would want to do this is because they might see that, oh, those pi's, if I could separate out this fraction, those pi's would quote unquote cancel, and so would the r's a little bit. And actually they do, right? Pi over pi is just 1, and r goes into r squared once. So if you did it that way, you would get a over pi r minus r, and that's equal to h. Both very equivalent answers, extremely acceptable in, well, in my courses. I don't know your instructor, but I would have to say this is very acceptable.